Okay, now that we're into similar triangles, we need to go over something called the triangle proportionality theorem. And before we actually talk about this theorem, I want to show you something with this diagram. So this diagram, we have two triangles. We have the little triangle on top, and then we have the big triangle, which is like the entire thing. And these little arrows, the little arrow on DE and the little arrow on AC, tell us those line segments are parallel. And one thing we've talked about recently is if those are parallel, then we've got some congruent corresponding angles on the left side and on the right side. So we know that the little triangle and the big triangle are similar to each other because of angle. So here's what that means. We can set up a proportion using the sides. So I'm going to mark some sides here, or mark some pieces of this diagram. So I'm going to call this piece from B to D W. From D to A, that's going to be X. From B to E would be Y. And then from E to C, I will call that Z. Now, if I want to set up a proportion using similar triangles, what I can do is take a side of the little triangle, so that'd be W, over the corresponding side of the big triangle. Now, the big triangle side is not W, it's not X, it's W and X together. It's W plus X. So W goes on top, W plus X goes on bottom. For my second fraction, I'm going to take the piece of the little triangle, the side of the little triangle, which would be Y. And then I want to do the side of the big triangle, which is Y and Z together. So it's Y plus Z. And then as always, these two fractions are equal to each other because they're proportional. So I can do that, but that's kind of messy. And depending on what numbers I get, what variables I get, that could be kind of complicated to work out and could give me a lot of extra work. So we will have to do that sometimes, but the triangle proportionality theorem gives us a easier way to deal with a situation like this, which does seem to come up a lot. So it's good to have another way to do it. So if you look at how this starts, it says if a line parallel, sorry, I'm blocking that with the pointer thing. Okay. If a line parallel to one side of a triangle. So that's the first thing we need is a parallel line or line segment. So on this diagram, it's talking about DE. That is parallel to a side of the triangle. It's parallel to AC. If that intersects the other two sides, so it hits at D and at E, it hits both sides, it divides the sides proportionally. So what that means is you can do this. You can set up a couple of fractions that are simpler than the ones we've already done. You can say W over X, so the top part over the bottom part, W over X, is equal to Y over Z. Again, the top part over the bottom part. And that gives you something that in most cases is going to be a whole lot easier to deal with than trying to set this up here. So we're going to go through several examples of this so you can see all the different things that might arise when you're dealing with problems like this. So here's the first one. It says solve for X. So I'm going to start with X, and I'm going to take X, that's the top part on the left side, and I'm going to put that over the 6, the bottom part, top over bottom. Then I'm going to go to the other side of the triangle and do the same thing with the 8 and the 4, top over bottom. These are equal to each other. Because we have parallel lines, we know that these parts have to be proportional. So now we can cross multiply 4 times X, 6 times 8, and then divide. So divide by 4, we will get X equals 12. So that missing part here is 12. And there's different ways you can check your answer. You always want to make sure your answer is reasonable. One thing I see here on the left side with the 8 and the 4, the top part is twice as big as the bottom part. So I should expect to get the same thing on the right. And I do. I have 12, which is twice as big as 6. All right, next example. Solve for question mark. So I'm going to start with the question mark. Now, the only thing I see on this top side of the triangle with the question mark is 20. And I want to be really clear what this is talking about. 20 is the entire distance from this point here all the way down to this point. So it's both of these pieces put together. So I'm going to take the question mark and I'm going to put it over 20. But I have to be really careful when I set up my other fraction. So on top of the other fraction, I'm going to put 3. 3 matches up with the question mark. They're both the sides of this little tiny triangle over here. But the bottom, 20 is the entire length, the whole side. So I need to make sure I do that with my other fraction as well. So I can't just put 9 because 9 is only a piece. I need the entire thing, the entire side of the big triangle. So what I'm going to have to do is put the 3 and the 9 together. And that's going to be 12. So it's going to be 3 over 12. So you have to be really careful setting up these fractions that you're really clear what every number, what every variable represents. Since 20 represents the entire side of the big triangle, the number on the bottom of the other fraction will have to represent the same thing. Will have to represent an entire side, not part of the side. So now we have this set up. We can work this out. I'm going to take 12 times the question mark, 20 times 3, get 60. We can divide by the 12, and we will find that the question mark is equal to 5. So our missing piece here is 5. All right. This one, it says to round to the nearest tenth. That tells us it's probably going to be a decimal. So here's one thing I look at here. I see 5 and 8. And again, 5 is a part, like the top part. 8 is the whole thing. It's from the top to the bottom of the triangle. It's the entire side of the big triangle. So if I wanted to set that up with x, and I put x on top, I would have to do the same thing over here and do the whole side of the triangle and add those together. So it'd be x plus 2. And I could do that. I could work it out from there, and I would eventually get the right answer. But that's going to be a lot of extra work. And using triangle proportionality theorem, there's an easier way to do this. So I'll leave that up there as one possibility, but here's the easy way. Since this whole side of the triangle from here to here is 8, and this part at the top is 5, I know that this part down here has to be 3, because 5 plus 3 equals 8. I just subtract my numbers. So now what I can do, instead of doing 5 over 8, I can do 5 over 3. And then when I match that up with the other side, it's going to be x over 2. So it's the top part over the bottom part on both fractions. That's going to make it really easy for me to cross multiply and divide and work this out. So I'll take 3 times x, that's 3x. 2 times 5 is 10. Now I just divide by 3. We will get, you do get a fraction or a decimal depending on which way you do it. This says round to the nearest tenth, so we'll change it into a decimal. 10 divided by 3, if you work that out by hand or put it in a calculator, you should get 3.3 repeating. So if we round that off to the nearest tenth, which is one number after the decimal, it would round off to 3.3. So x is going to be 3.3, 3 1/3. All right. Next one here, very similar situation. We on the right side we have the 8 and the 28, and we could set that up by putting 8 over 28. But again, we're going to save ourselves some work if we can just figure out what the length of this piece here is, from K down to this first parallel line. And so we can do the same thing we did before. We have a 28 is the whole side from K to L. 8 is the bottom part. We just subtract that, 28 minus 8. And that tells us that the missing piece here is 20. So now we can set up our two fractions by doing the top part over the bottom part. So we'll take 3x minus 5 over 10, and we'll take 20 over 8. We will cross multiply. Now here, because 3x minus 5 is an expression with two terms, so when you cross multiply with the 8, you'll need to put 3x minus 5 in parentheses, and you'll have to use distributive property. Otherwise, if you don't do that, it's going to throw off your answer because the 8 will not get multiplied by the entire thing. You have to make sure the 8 gets multiplied by the entire 3x minus 5. We got 10 times 20, that's 200. 10 times 20 is 200. Okay, so I distribute my 8. 8 times 3x is going to be 24x. 8 times 5 is going to be 40. So I have 24x minus 40 equals 200. I can add 40 to both sides. I get 24x equals 240. And now I can divide by the 24 and figure out what x is. And x is equal to 240 divided by 24 is going to be 10. So x is equal to 10. And if I want to kind of check and see if that makes sense, I can plug it back into this angle here. So 3x minus 5, I'll take 3 times 10 minus 5, and that gets me 25, which seems pretty reasonable. 25 and 10 on the left, 20 and 8 on the right. All right, last example. So we're talking about triangle proportionality theorem. You'll notice this diagram, it's not actually a triangle. There's no actual triangle here, but the same principle applies. We've got 3 parallel lines here in this situation, and all these parallel lines cross these 2 lines here, these 2 somewhat vertical lines. And so what's going to happen here is the parallel lines are going to divide the pieces of these other 2 lines proportionally, just like they did on the triangles. And so what we can do is we can just set up x, like 10 over x, so top part over bottom part, and make that equal to 8 over 6. So 10 over x equals 8 over 6. This is actually going to give us a decimal too, but it'll be a nice one. So what we can do now is just cross multiply. 6 times 10, 8 times x. So we get 60 equals 8x. So now we just divide by 5, or we don't divide, I don't know why I said 5. We divide by 8 because that's the number that we have to divide by. We divide by 8. 60 divided by 8 ends up being 7.5 exactly. And so that's what x is going to be equal to, is 7.5. So if you see a situation like this, even though it's not a triangle, it works the same way. If you've got parallel lines like this, it'll split these other lines into proportional pieces, so you can make fractions by taking the top part over the bottom part on both lines. So that's what we're doing with triangle proportionality theorem, and that's how it relates to some of the stuff we've done with similar triangles.